Hey guys, welcome to my channel. I guess I'm hoping to do this recurrently, but I want to have this as a place to talk about system design and design coding. I'm currently studying a lot myself and I feel like I've learned a lot in the process. So yeah, let me give you a quick introduction about myself and why I'm doing this. I'm a senior software engineer and I develop high volume services on a daily basis. And yeah, there's a few reasons I want to make this channel. One is that I'm a narcissist. I like the sound of my own voice. But two, probably a lot more importantly, is that I find a lot of existing resources, especially YouTube videos, are for people who really oversimplify things when it comes to designing systems. They be like, okay, let's build this Facebook Messenger. Then they'll talk about all the design choices you have to make, going into basically zero details on why they choose one technology versus another. And that really frustrates me because I would like to see deeper dive on it. I feel like you kind of just a sham if you just regurgitated some YouTube video, and if your interviewer is like any amount of smart or skeptical, he'll just ask you why you made the choices you did, and you're not going to be able to answer. So, I think part of that is doing more of a fundamental dive onto how these technologies actually work before going into, full scale system design example problems. And that's what I'm planning to do. The third reason is I believe fundamental computer science knowledge, like all these data structures and algorithms, operating systems, is and will be essential part of being a great software engineer. So without further ado, let's talk about in-memory cache today. And yeah, hopefully it helps you guys out. Okay guys, let's get started. Today we're going to talk about in-memory cache, and specifically we're gonna be talking about LRU cache. So first, what is cache? Cache is something that has two API endpoints, right? API functions. First, get, okay, fetches the information from the cache, and the second one, puts the information into cache. And the time complexity of these operations should be constant time. And prerequisites of this tutorial would be like a knowledge of linked list data structure and hash maps. Yeah, that's it. If you look at cache, you kind of we already have like a data structure that lets us do these two operations on at constant time, right? And it's hash map. It lets us look up the keys at a constant time and update the keys at constant time as well. But how cache is different than just using a hash map in any programming language? The main difference, I would say, yeah, like cache is not unlimited. It should be bounded. So and the bound can be like number of items in the cache or the size of the cache, the actual memory size of your cache, like 2 gigs or 10 gigs or 10 megabytes. So yeah, that limit or constraint makes your hash map, for example, a cache that you can use. So there's a question arises: what happens when the hash map or cache is full, right? We need to delete. We need to start deleting items, and in order to start to delete items, we need to answer the question: which items should be evict? So there's a term evict. And in caches, especially in memory caches, there are eviction policy types: LRU, LFU, etc. Today we're going to be talking about LRU. So basically what LRU stands for is least recently used. So when we start deleting items or evicting items, we start evict the least recently used one. So the oldest ones. Imagine we have the items sorted in timestamps by their timestamps, like this, and we delete the oldest one. So, okay, as you can see, this is our cache, and this, currently what you see, is our memory. And when I say we keep items in memory, these items, like you see, will have key. I'm gonna make this tutorial and the code of it as close to production as possible. So I'm gonna use string as key, and value would be something of type value. Like it can be anything as long as it implements this value interface. More detailed on it later. So I'm gonna keep the items of the cache in my memory, and I wanna keep them, store them, sorted by their timestamp when they were actually created inside cache. Okay. So basically, I'm gonna show it here. I want to keep or store items sorted by their timestamp. This came in time 0, this came in time 1, this came in time 2, this came in time 4, for example. And each item will keep a pointer to the next one. Okay, next one. And the last one would be the most fresh, in our case, fresh item. Newly created, and it will point to no. Okay, because there's nothing on its right side. So this is how I'm planning to keep the data, keep items. Also, in order for us to create a LRU data structure, let's call it data structure, right? And this data structure should have several properties. Like, first of all, I want to have these items, right? And I want constant access to its head of this list. Actually, I want constant access to any of these items. But because I'm sorting them by their timestamp, yeah, I want to keep them as linked list. Okay, so our LRU data structure will have list. I'll call it LS, which is going to be linked list. Linked list of items. And another thing is I would call table, actually the hash map, right? Which will be string key as a string and value something of type value. And that value is an interface that implements size, which returns, in my case, in Go, integer 64, the size of the value, actual value, okay? So this will be table, and this value, actually, I don't want to keep values here. Eventually, we're gonna end up getting value from the value. Yeah, no pun intended, but I want to keep the items as value here. So basically this table will be pointing to these items. Okay, this table. And inside of this element, thus inside of this item, we have key and value as well, and the size. Yeah. So basically, other than this, we're gonna have like capacity, as I said. Cache is not like hash map. We can do it with hash map if we don't have capacity, right? For cache, we have to have capacity. So I'm going to keep it simple with integer, some like number of bytes. And of course, the size of the current size, the actual size of the actual memory of our LRU cache. We're gonna track that as well. So yeah, here I created use cases. So first use case or API function would be like get function, and then that function gets key as argument and gets the value. And basically what it does is we look up the key in our table. And if key exists in the cache, we move it to the end of the list and return. So why we move this element? Let me delete this not value, but I would say item. So it's easy to understand this item. So as I said, I move it to the end. Why? Because I said I want to keep items sorted by the timestamp, right? And every time I get one item, which might be oldest one or the second oldest one, if I read it or fetch it once, this is no longer the oldest one or the second oldest one. This should be the fresh one. That means it should move here, okay? Because it's just been accessed, and the last time it was accessed, like just fresh, it was recently. So this becomes the most recent one, and now this is the candidate to be evicted. Okay, so anytime we get or even put, when I say put, when we, for example, updating of currently existing items value, we need to move it to the end as well because it's been accessed. So it is kind of actual. Okay, that's why we move it to the end list. So every item we fetch or put will get added to the end list, meaning it is the freshest one, it is the newest one, and the oldest one will be on the left side or the front of the list. Okay. Otherwise, if we don't have it in the cache, we just return no. And the second case, which is more like I would say complicated a little bit, is we again look up the key in the cache in our table, and if key is present, we update its value. If key is present, we update its value, move it to the end of list, and calculate the size difference between the old and new values. Difference variable, increase LRU size by diff. So as I said, we are keeping the size of the actual size of the cache, the overall cache, and the capacity that it can hold. So every time we update a key or insert a key, we need to increase the size of the cache. Okay, when we update, we need to update the size of the cache as well by this value, whatever it is. It might be positive or negative as well. So check if LRU size exists the capacity. This is a checking operation. So every time we make like updates to our cache, like by whatever, creating new items or updating existing ones, we need to check whether the capacity or the size of the cache does not exist capacity. This is kind of, I'm imagining this is going to be another like separate function that does that, because we're reusing it here as well. So when the key is absent, it means we need to create a new item and just add it to the list and update the table as well. With this information, let's get started with coding. And I will be using Golang to actually implement this. Yeah, I have a directory ready for it. So yeah. First of all, I want to start, as I said, I want to keep this as close to production as possible. So I want to start with defining an interface for the cache. Okay. And for that, I'm going to create a separate directory inside of which I'm going to create cache go. And this cache will contain the interface named cache. Okay. Because currently I'm only providing two API functions, get and put, as you can see. So get will be like I think it will take string and it will return value. Okay, and this value I'm gonna create it again here. This is something that has size in it. Okay, it's an interface and it has size function. Actually, let's make it 64. It can be large, and the cache will get. Let's make it value and also boolean, indicating whether the key is there or not. And another second function is put, and takes key and value. Okay, key in this case will be string and value will be value, and does not return anything. So we need to kind of implement this interface, and the implementation can be different, right? It can be a LRU cache or LFU cache. For today, I wanna show you least recently used cache. So it could be LRU. Okay. So I'm going to define this as a data structure, LRU, which will contain these fields in it. Okay. I'm going to create this item as well, because these are the actual items that are residing in our memory. Okay, let's start with the LRU cache. A LRU cache will contain ls as linked list. See, I'm marking as linked list, and in Go we can access double linked list from its container standard library, which is list. I don't want to like reinvent the wheel here. I just use the ready-made ready data structure. The table would be hash map key to item. So I'll just call it table as well. It would be map of string to something called pointer to item. And that item would contain key, and that's not struct, it's struct, not interface. Key and value, which would be value, like value would come from this place, right? And also I would like to keep the size in integer 64, all right? Size. So LRU cache, besides this, has capacity and size. Capacity would be this, and size as well. Okay, and yeah, I'm going to quickly define a constructor function, new, that will return LRU cache, pointer to LRU cache. Okay, and the constructor is where we get the capacity, because it's going to be initializing function. So I'll just take it as S. So yeah, capacity would be S and size would be 0. We're gonna meet it, just okay. And list would be newly initialized list, and table would be again, yeah, string to pointing to item. Yeah. I think we have the structure currently, and we can get started with the implementation functions, implementing the API functions. So let's start with get. I'm going to create a method. I'm going to create this type LRU cache, and this is get, right? This will get key, and this will return value, which is coming from cache package, and returns boolean indicating whether the item is there. Look up the key, okay? So everything we do, I want you to pay attention. Everything we do inside these two API functions, whether get or put, should be constant time, okay? So, or at least should be constant at amortized constant time, okay? So let's continue. If continuing cache, if entry or item. By the way, I'm not gonna be able to access because I'm using like this data structure list and its elements, like these elements. You see elements, right? The elements should be something that this data structure can work with. It actually already has the elements in it, like root elements and everything it contains should be element. So table that actually will actually contain to like point to the element instead of the item, and that element has value in it, which can be anything, and that value will contain pointed to our item, which will then contain key and value here. Okay, this is coming from standard package, standard container list. Okay, let's yeah, I'll call it entry, this table, like key. Okay, and if entry is going to be null, right, then we'll just return null and false. Otherwise, that we just return entry dot value, we cast it to item and value, return the value, and second this will be true. So but as I said, if exists in the cache, we'll first move it to the end of the list and return. So yeah, we need to move this entry, move to back this entry. Yeah, our linked list has built-in functions that are super handy, and that lets us manipulate the entries or elements inside of it. Okay, so I think this is basically it for our get function. For put function, put will get key as string and value as value. It does not return anything. So first we again look up the key. Okay, we'll look up the key the same way we did before. Okay, if the key is present, we update its value, move the entry to the lens, calculate the difference, increase the size. All this should be, I think, should be like extracted to its own method, right? So if entry is not null, means we have the key. Update the key. Otherwise, we need to insert new item into our cache. How about it? And these functions, this implementation, I'm going to implement in separate private methods. Okay, let's do it. You know what? Let's keep it simple for now. Just do it here, then I'll extract later. Okay, update its value. So, no. First, we need to get the item of the entry, right? So, item would be entry dot value. I'm gonna cast it to item. So item dot value would be value. Yeah. Then calculate the size difference between the old and new value. So because we're updating in this case, key exists and we're updating its value, and that value can be larger or like smaller than the one we already have, right? So we need to get the difference between the two. I'm gonna call it diff, or let's be more size diff, and this diff will be size difference between the current one, the new one, minus the old one. Item.value, item.size. And this size should be added to the overall cache size. Like this size difference can be can end up being a negative and or positive as well. If the new one is greater than the old one, the size difference will be positive value. And we actually increment the size. Otherwise, we decrement the size here. So increase the LRU by diff. Yeah, I increased. Check if LRU size exceeds its capacity. Here, I think we're gonna do the check. Check if size exceeds capacity. Yeah. Okay. What else? What else? What else? Yeah, we did not move it to the end list. So let me quickly do it. This list move to back entry. Okay. So here, in other case, if the key is absent, means entry is null, we need to create new item and insert it to our cache. Create a new cache item with a value. Okay. Item would be item key value size. Because this item, remember, is just 3-word structure, key, value, and size. We'll create it here. Then we gonna update the LRU table and update the LRU size. Actually, I want to add this to our pushback to our list as well, right? And I want to update the table. So table of key would be pointing to this pushback item returns the element, as you can see. We pushed it and the element should be stored in our table, in our hash map. Okay. And we should update the size. Current this size plus item.size. And also here we need to check. The same check should happen here. Yep. So same check should happen here. I'm gonna externalize that method into a private method of this little cache. Check, like let's call it check capacity. And this will do the actual eviction process as we talked about here. When the size of the cache exceeds the capacity it can hold, we need to start evicting, and we evict as I told you, the oldest items. Okay, the oldest items. So we're gonna be evicting items as long as size is greater than capacity. So that logic should be implemented here. So I'm gonna iterate until or while this size is greater than this capacity. Size exceeds the capacity. I'm gonna delete this, remove the front of the list, the items in the front of the list. Okay. For example, this is if this was the list and this is the oldest one, this should get evicted. And the remove function returns the actual value of the element it just removed. So we're gonna item deleted, should gonna be this one, and we need to update the table as well. We need to delete it from the hash map as well. Okay. So here, this dot table and item deleted dot key. because we are casting here, then we have access to key. Okay. So we're deleting the front of the list, getting the item, and deleting it from the table as well. So at this point, we need to decrement the size by size of this deleted element. Okay, and this method actually makes the for stop. Okay, every time it deletes an item, it subtracts the size of that item from the overall size, and yeah, eventually it will break out of this loop. So I will just call this function now inside our update and create new values as well. Oh yeah, as I promised you, let's extract it to new method and call this new method update item. Okay, and this should be create item. Here we're creating it, and here updating it. So item value is being updated, it's been moved to back, and the size difference is being reflected as well. Great, great. I think we're good at this point. So now let's test it. Okay, simple test for now. LRU is gonna be cache dot cache, right? And we're gonna call LRU dot new. LRU dot LRU cache. I'm gonna get LRU cache. And LRU dot new is our constructor function, takes size. Let's call it 16 bytes for now. Okay. And actually, if we want to put something to it, okay, key is like string, regular string, but the value is cache.value. We need to create a type that satisfies this interface, or in other words, implements that interface. And I'm gonna quickly create that type. It would be like regular integer type, int type, or int value with the method int value method, and which has size and returns the size. And the size of the integer would be, I'm gonna do it dynamically by calling unsafe size of function of this. And I'm gonna just cast the regular integer to this type. And I'm putting key 1, key 2. Okay. I think this returns because my MacBook 2 integer, the integer size depends on your like architecture, compiler, and on your machine. And currently my machine has the size of integer as 8 bytes, so it should be 8. So in this case, each value 8 bytes, and a LRU cache can only contain like maximum 2 elements. Okay, we implemented this, and this is our and let's check it, let's run it. Okay, you just run, but how to check? Let's make LRU cache get actually. It will be val and okay value, right? Okay, just yay. This is the value, this is the true. Has it. Key 1. And let's make the second key. Yeah, it is there. Both keys exist. Remember when I said when we get, we make this operation. We move the entry to the end list, basically saying it is the newest one. Okay, so when we get key 1, although at this point it was the oldest one, after we got it or fetched it once, K2 now becomes the oldest one. So at this point, K1 again becomes the oldest one. Okay, so if we add another K3 with a different value, for example, it will cause our check capacity, because it's the size, the current size exceeds the capacity it can hold. Okay, so at this point it is just 16 bytes, like 8 bytes, 8 bytes. The third one will exceed, it will be 24 bytes, right? And we need to make a room or delete until we satisfy this condition. So, and at this case, the front of the list will be deleted. So which is K1. Okay. After doing this, I'm going to go ahead and try to access K1 again, and I should not see my K1 because at this point, at this very moment, the K1 should be evicted. Okay, let's run it. Yay, K1 is not there. Beautiful. So in order to make our life easier, we can put like debugging message evicted and item deleted. Yeah. This way we can see which item got evicted. Evicted key 1. See? Beautiful. So the constraint of the LRU cache is in bytes now. And whatever new type you create, be it a struct or any other type, as long as you implement this interface, which basically has one method that returns integer 64, you're good. You can have it as value and store it in our LRU cache. Because based on that value, for example, if you want just the number of items instead of like bytes, just make it 1 here, okay? And this will be no longer bytes, but number of elements we can hold, okay? I think this is really cool, however you want. So yeah, just keep that in mind. Whatever value, just implement this interface. You're good to put that as value here in our cache. And in real world, I would also add, as you might have already guessed, synchronization primitive in order to serialize concurrent access to our data structure. And that would be sync mutix, right? And I would call it here lock. I would defer these unlock, and I would copy that here as well, so that the access to our data structure is serialized, and now it's safe. Yeah, that's basically it. That's basically it. So in this second episode of this video, I'm going to create a LFU, which requires LRU knowledge as prerequisite, because it'll be LFU is a little bit complex than LRU. So now I want you to just know how to create LRU on yourself. Okay. So if you like the video, please, I'll be happy to hear your feedback. Yeah. Happy coding.